Enterprise networks require redundant physical links to survive hardware failures. If one cable snaps, another must carry the load. But at layer 2, this physical mesh creates an immediate mathematical problem. Because Ethernet lacks a built-in mechanism to track the lifespan of a frame, redundant paths allow data to circle the network endlessly and multiply uncontrollably. These continuous cycles result in broadcast storms. A single broadcast frame duplicates across the mesh, saturating bandwidth and forcing switches to continuously overwrite their MAC address tables until the hardware crashes. To prevent collapse, we use the spanning tree protocol, or STP. STP mathematically overlays a loop-free logical tree directly on top of the physical mesh. With a central root bridge elected, STP evaluates every active interface, assigning each a strict mathematical role. STP assigns every interface into one of 3 mutually exclusive categories: the root port, the designated port, or the blocked port. These roles dictate exactly which interfaces are allowed to forward traffic and which must remain disabled. They are the calculated outputs of a decentralized algorithm that forces a cyclic physical network to operate as a safe acyclic logical tree. The algorithm begins with a strict requirement. Every switch that is not the root bridge must select a single definitive upstream path leading back to the root. Switches cannot guess the best route. They determine it using a specific metric: cumulative path cost. A non-root switch connects to the root bridge via 3 links. STP assigns a mathematical cost based on bandwidth. Slower links carry high penalties. Fast gigabit links have low costs. The switch sums these values across every hop, generating a cumulative total for each route. The outcome is absolute. The local interface attached to the path with the lowest total accumulated cost wins the role of root port. To prevent upstream loops, the algorithm enforces a rigid structural constraint. Each non-root switch is permitted exactly 1 root port. That single root port acts as the switch's definitive center of gravity, ensuring that all upstream traffic utilizes the most efficient route available. With the upstream route secured, the algorithm shifts its focus to downstream delivery and the challenge of shared network segments. Every link between switches is a shared collision domain. To prevent redundant delivery, only 1 port can forward traffic. The switches compare their distances to the root. The one with the lower cost path claims control. That winning interface becomes the designated port. At the very top of the hierarchy, the root bridge encounters a mathematical exception. Its path cost to reach itself is exactly 0. Because no other switch can beat a cost of 0, every active port on the root bridge automatically assumes the role of a designated port. By isolating segment authority to designated ports, STP guarantees downstream traffic enters a link from the single most root proximate source, completely eliminating duplicate frame delivery. Now we pull back to evaluate the entire network topology with the root and designated roles successfully assigned. Looking at this map, active pathways form a clean tree, but several physical links remain unassigned. If these remaining interfaces forward traffic, the logical tree will collapse into a loop. Therefore, they become blocked ports, placed into a strict discarding state, dropping all user traffic. These disabled links are not wasted infrastructure. They are active, listening standby paths continuously monitoring the network for topology changes. Blocked ports resolve the paradox of redundancy. They provide the mechanism that preserves physical hardware backups while rigorously enforcing logical safety. This comparison shows the total mathematical outcome. A chaotic physical mesh on the left filters into a clean, finalized logical tree on the right. The rooms are absolute: 1 root port per non-root switch, 1 designated port per segment. Remainders are definitively blocked. When an active physical link is severed, the network demonstrates its dynamic resilience. A standby blocked port detects the failure, reevaluates its role, and transitions into an active path to restore connectivity. This recovery happens without any central controller. The network relies entirely on the decentralized cost logic to reconverge. But there is a critical operational danger. If a blocked port transitions instantly, it risks creating a temporary broadcast storm before the rest of the network can finish updating its routing tables. To prevent this, STP forces the interface through a built-in delay mechanism before it is allowed to transmit user data. We call this mechanism STP port states, a sequence of listening, learning, and forwarding phases that we will investigate in the next video. Port roles mathematically define the safe destination for traffic. Port states dictate the cautious journey required to get there without crashing the network.